Hi, today I'll be reviewing AP Chemistry Unit 1, Atomic Structure and Properties. This will be the third installment in my AP Chemistry review series, and I hope to get all the videos done by May 2nd. So, Unit 1.1, Moles and Molar Mass. So, particles are extremely small. And so what researchers needed was a way to get the same amount of particles with different weights together. So they came up with an idea called the mole. And this number is basically 6.02 times 10 to the 23rd particles. And that's extremely large. So the thing is, all particles weigh differently, and basically, in order to convert the amount of moles into a weight like grams, there's something known as the molar mass. And there's a different molar mass for each element in the periodic table. And the periodic table has the molar mass, or the weight of one mole of an element in grams, in either the top or bottom of each element. So let's do a simple problem with finding the molar mass of a compound. So this compound is called sucrose, and what we're going to do is we're going to find the molar mass. So what you have to do is you have to get the subscripts, and you have to multiply each of them by their respective molar masses. So the subscript of carbon is 12, the subscript of hydrogen is 22, and the subscript of oxygen is 11. And what you have to do is you have to multiply each by their respective molar masses. So the molar mass of carbon is 12. Molar mass of hydrogen is 1. And the molar mass of oxygen is 16. You then just multiply them. So 144.2 and 176. And you just add them all up. And that gives you a total of 342. I just can't write today. My bad. 342 grams per mole. And another thing you have to know is conversion factors. And conversion factors are basically a fraction between the mole. And it just shows the relationship between the moles and grams, and grams. And you can flip these. You can flip the fraction to have it be 12 grams over 1 mole. And these are basically extremely useful for stoichiometry. You can't do stoichiometry or dimensional analysis without them. So 1.2. So mass spectroscopy. So mass spectroscopy is used to calculate the atomic or molar mass by examining the abundance of isotopes in elements. So in order to do this, you have to multiply the percent abundance by its mass and add all of them up in order to get the total mass. And then you have to use a periodic table to verify. So let's try this problem. So for this one, what you have is you have the mass of 35 grams, which is an isotope, chlorine 35, and you have 37, which is chlorine 37. And what you have to multiply these by is the percent abundance. So for 35, you have a 0.75 as your percent abundance. And for this one, you have 0.25 because it only goes up to 100. So this. And this will just be 37 times 0.25 would just be 9.25. And 35 times 0.75 would basically be 26.25. And the total would just be 35.5, which is close to 35.45, meaning this is chlorine. And most problems like these will not have the name. So if you were going to do another one like this, you would just cross out the name. Yeah, so I just can't draw today. Yeah, so I guess that's pretty much it for problems like this. So just one piece of advice I would give when doing such a problem is to just try to estimate it as the best and the closest as you can for percent abundance, because if you just mess it up a bit, it'll change the grams, and that will make finding the molar mass much more harder, and you have a higher chance of getting something wrong. So for all drawings, 1.3. So all pure elements have a fixed composition. For example, sodium bromide has a 1-to-1 ratio. So what we're going to do is we're going to find the percent composition of a substance. And what you do is, so for this example, you have glucose, C6, H12, O6. And you have to find the amount of carbon in glucose. So what you do is you just divide the amount of carbon by the molar mass of glucose. So the molar mass of glucose is 180 grams per mole. And the amount of carbon is 12 times 6, of which 6 is the subscript and 12 is the molar mass. So that'll just be 40%. As it's 72 divided by 180. So another thing in 1.3 that we have to know is empirical formula versus molecular formula. Both the empirical and molecular formula have the same ratio, and the empirical formula is basically a simplified form of the molecular formula. So let's try a problem of this. So what we have is that a compound is determined to be 43.6% phosphorus and the remainder oxygen. What's the empirical formula of the compound? So what you have to do first is you have to convert the percents into grams. And first you have to know how much percent of oxygen there is. So it's 43.6% phosphorus and 56.4, I believe, percent oxygen. So now what you have to do is you have to convert this to grams, and that you just put G, because it adds up to 100 grams. So you just make it like it's 100. So now that you do this, what you have to do is you have to convert all of this to moles. So 1 mole of phosphorus will basically be 30.9 grams. And 1 mole oxygen is 16 grams. And so the molar mass is, I'll calculate it right now. So 43.6. And that's 1.45. And the molar mass of oxygen would be 3.52. And now what you have to divide is you have to use these and divide by the lowest number of moles in order to get the mole ratios. So 1.45 by 1.45 is 1. 3.52 divided by 1.45 is 2.5. Now, as you can see, you can't have a 2.5 as its subscript. It just won't work. So what you have to do is you have to multiply both by 5. So the mole ratios will be 2 and 5. So now what you have is P2O5. So in order to do problems like this, I would just use the table for the first 1 or 2 problems, and then once you start getting the hang of it, I would recommend not using it, as it takes a lot of time. But then to just get started, this is extremely useful, as it basically gives all the steps. So 1.4, composition of mixtures. I don't have too much for this one. So mixtures contain more than one substance, and they have variable compositions depending on the amount and type of substance in each mixture. One example of mixtures are solutions, and the problems that the AP test will give you on this is mostly just seeing whether what is a mixture and what is not. And along with that, they may, I'm not sure if they will. I haven't seen much problems like that. They may have you do like a type of stoichiometry problem relating to this. I'm not too sure though. So 1.5, atomic structures and properties. So atoms have a positively charged nucleus, protons and I made a mistake. I'm sorry. Protons and neutrons surrounded by negatively charged electrons. So Coulomb's law is basically showing the relationship between the force and the amount of and the distance between the electrons. So basically, like the simplest way to put it is the larger distance there is between two electrons, the smaller the force, and the smaller distance two electrons are, the larger the force. So this diagram is basically just showing it. So electrons closer to this one is closer to a nucleus, so it requires more. So it requires more energy to remove, while this electron over here is further away from the nucleus, so it takes less energy to remove, and this would be considered as a valence electron. And this sort of problem is extremely important. You'll probably see it on the AP test at least 1 or 2 times, and it's important to try to get it as best as you can, because like I still don't get it too well, so yeah. So 1.6, photoelectron spectroscopy. So electron configurations. So PES basically uses subshell notations in order to determine the energy required to remove the electron. And the height of peaks over here are directly proportional to the electrons in the subshell. For example, you have like peaks like this that are smaller, then that basically denotes the 2 subshell. Well, S subshell, my bad. And then P subshells are much higher than that. And basically this diagram of the periodic table just shows what you're going to use for like S, P, D, and F. And HE is also part of the S subshell. Oh, that's shown over here. So yeah. So let's try a problem with this. Okay. So first of all, what you have is you have to find the ground state electron configuration of silicon. And basically what you have to do for this, you have to get a periodic table out. And I'm just searching it up right now. And let's go back. Let's use this one. So basically what you have is if you have H and HE, that's 1s2. And you also have Li and Be, which is 2s2. Then you have boron to neon, which is 2p6. Next, you have sodium and magnesium, which is 3s2. And also these are supposed to be on the top. My bad, I'll fix it after. And lastly, you have to get to silicon, which is just 2, so it's 3p2. So I'll just fix these up quickly and just a sec. This 2p6, 3s2, 3p2. So that's the ground state electron configuration of silicon. For all drawings. So let's go back to this one. So problem 2. So this is an AP problem from AP Classroom. So thank you to College Board for providing all of this. So first of all, what they're asking us to do is to write the ground state electron configuration of the element. So what you have is you have the small peaks, so which is 1s2, 2s2, 2p6. I keep forgetting, my bad. 3s2, 3p6, and 4s2. And basically it becomes a pattern once you get it. So yeah, and then so now you have to identify the elements. So once you use a periodic table, so it's it's hydrogen, helium. Then you have lithium, beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, neon, sodium and magnesium, then aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Then it will just be potassium and calcium. So the element is calcium, Ca. For this, you'll have a periodic table, so it's not too much, like you don't have to memorize anything. I still don't have, like, I can't, like, I know the elements, I just don't have it memorized. So 1.7, periodic trends. So the four main periodic trends that you have to know is atomic radius, which is the size of the atom, ionization energy, which is the energy required to remove an electron from an atom, electronegativity, the ability of an atom to attract shared electrons to each other, and electron affinity, energy change when an atom gains an electron. So the thing is with atomic radius, with larger atomic radii, there's a weaker attraction between the valence electrons and the nucleus due to a greater distance between the nucleus of one atom and the electron of another, and they have a smaller electronegativity. And with a smaller atomic radii, you have a stronger attraction due to a smaller distance between the nucleus and the valence electrons and a larger electronegativity. And along with that, you have metals electrons are easier to lose because the nucleus have a strong attraction to the valence electrons. Along with adding electrons is endothermic or slightly exothermic. The electron affinity is positive or negative. For nonmetals, it is easier to gain electrons because the nucleus has a stronger attraction to valence electrons. Adding electrons is exothermic and the electron affinity is negative. And this diagram of the periodic table basically shows, sorry, my bad. It basically shows everything put into a diagram form. I would recommend it's honestly quite easy once you get it, but they'll ask you some questions on the types and all of that. So it's better to know your stuff well. I would also recommend watching the AP Daily video on it, as it's also pretty good. So here it is. I'll just give you a second if you want to copy it down. So 1.8, valence electrons and ionic compounds, the last one. Ooh. So valence electrons are basically in the outer shell of the electron, and this subsection just talks about how to use a periodic table to get the charges of valence electrons. And one easy way of remembering it is that just knowing that like alkaline metals, alkaline earth metals and metalloids such as this one, this table, they all have plus charges. So +1, +2, +3. And these three tables have negatives. So -1, -2, -3. And one other one is carbon-4. So I would recommend, the best thing I could recommend doing is just memorizing all of the ions. Just try your best to do so because it makes life so much easier during the AP test. Most people say you don't have to, but I mean, it's like you're an AP Chem, it's like a college level class. Like it's best if you do know it because it just reduces time. So I guess that's pretty much it. So just acknowledgements. So the credits for all the pictures and problems go to College Board except for one of them. And thank you for everyone for watching, and just stay safe and good luck with your AP tests.